Let's now discuss how to apply our fundamental principle, Newton's second law, to an observation of motion in the real world. We'll start by extracting motion data from a video of an object moving in the same direction at the same speed, the case of constant velocity. We encourage you to work through on your own the steps we discuss here. You will use many of these same steps in future labs, beginning with the first lab, where you will obtain data for constant velocity motion that you will observe. To do the video analysis we discuss here, you will need to run the software application Tracker. And you will need to download files at the link, which should pop up now. Now, before we get into details, let's briefly remind ourselves where analysis of motion on video fits in the way we think about doing physics. What we'll talk about today falls squarely in the realm of investigation. We're discussing here how to extract quantitative data from motion captured on video. Let's start by running Tracker. From within this application, let's find and open the file named sample.mp4. We can run this video and see that it shows a soccer ball rolling from right to left. Now, the first step in our analysis is to specify the video frames which contain the motion we're interested in. So to do this, we're going to select the range of images that, to our eye, shows the ball moving in the same direction at the same speed. We can click and drag the bar, scroll bar at the bottom to the beginning, and move the black arrows at the bottom to position it first at the first frame that we want to analyze, and then the second black arrow to specify the end frame.
We want to skip the first few frames at the very beginning because the ball is speeding up from rest, which is not the constant velocity motion that we are interested in. That's why we've selected to start at frame 22.
Other good choices of range are possible here. Next, we need to specify and check the video timescale. Video cameras typically record video frames at regular time intervals. Tracker will attempt to read the time between frames. That information can be found by clicking on the clip icon located on the toolbar at the top. Here, the frame rate is reported to be 30 frames recorded per second. This means the time between each frame is 1/30th of a second. I know that this is correct for the camera used to record this video. However, there are times when you may need to specify this for your own camera, so it's a good idea to check this. We can also see here the range of video frames that we will analyze.
The black arrows beneath the video bar show the section of the video we've selected to analyze.
We also need to specify now the length scale in the video. To do this, we need to insert a calibration stick and set the endpoints to something of known size in at least one video frame. When we select the calibration stick, we can do so by clicking on the stick at the menu, the top of the toolbar. And when we do this, we see that we have the blue calibration stick with endpoints appear in the middle of the frame. Here, we'll use the soccer ball's diameter as our known length in the video. We move the stick's endpoints by left-clicking and dragging the endpoints in such a way that we span, so that the calibration stick spans the soccer ball and the stick passes through the center of the ball. We can click at the top and zoom in to get a better look, to more carefully place the endpoints of the calibration stick. Now we have to explicitly set the length of the calibration stick. Now we know that the length of a diameter of a standard soccer ball is 22 centimeters. So we'll insert that here. But we also need to explicitly specify which units we're going to use. So here we'll use SI units and specify the soccer ball's diameter in meters. Now, sometimes you'll see that the length of the stick appears in scientific notation, so be sure you are aware of this. Finally, we can make the stick disappear by going to the top menu and clicking once again on the calibration stick menu. The calibration is still good, even if you can't see the stick.
If we want to make the calibration stick visible again, we need to click on the icon once more and it will appear.
Next, we have to choose the coordinate system in which we will describe the motion. So to do this, we can click on the axes, first zooming back out. Click on the axes located on the toolbar at the top. The axes appear where the origin is by default in the middle of the entire frame, and the default orientation of the axes is such that the x-axis is positive to the left and the positive y direction is toward the top. Now we are free to choose the origin and orientation of our axes, so we'll do that in a way which makes sense for this observation. Let's place the origin of the axis at the center of the ball.
In the first frame we're interested in, frame 22 in our case.
We do this by left-clicking and dragging the origin to place it at the ball center. Now, origin will now be fixed for all frames, even as the ball moves. Now, if we wish, we could tilt the axes by left-clicking and dragging the short vertical bar located on the positive x-axis. We're going to keep the original orientation of the axis as is for now, where the ball now moves along the x-axis in the negative x direction. Once again, we can make the axes disappear while still remaining in effect by clicking again on the axes icon on the toolbar. We are now ready to extract position data for the ball. The motion we're interested in is the translation of the ball, so we need to identify the average position, the center of mass, of our object in each frame. To do this, we'll click on the word Create on the toolbar and select the Point Mass option. This creates a legend marked Mass A with a diamond symbol. For the current frame, we now move our cursor to over the average location, the center of the ball. We hold the Shift key down and then we left-click on the center.
Then we release the Shift key.
And we see that the frame advances and that a symbol, a diamond symbol, is left behind which marks the average location of the ball in the previous frame. This location is stored in a table that we'll look at in a moment. We can continue in this fashion, continuing to mark the average locations of the ball frame by frame.
Remember, if we want to track the position of an object, we will have to hold Shift and then left-click.
We repeat this process, and when we get to the last frame, we should see something that looks like this. When we reach the last frame, the video no longer advances, and we have now obtained position data at different times for our object. At this point, it's a good idea to save our analysis in a tracker file, which has a .trk extension. Let's mention here as well that more details on the steps we discuss here can be found by selecting the Getting Started option under the Help menu at the top. Now, Tracker shows a position versus time graph as well as a table. Often we will extract the data from Tracker by cutting and pasting and plot that data elsewhere, say in a spreadsheet. We'll discuss that later in a different lecture. Right now, at the end of this lecture, we'll take note of some key results from our analysis. We see that, for example, at the start of our observation, we set our clock to t equals 0. And at that time, the ball's x position is 0.001 meters. So let's go ahead and record that data. Note here we're writing the ball's initial position as a position vector in component form appropriate for the coordinate system we chose for our analysis. Let's also now estimate the ball's initial velocity. We can do this from the data. We've already recorded the start time, initial time, and the initial position. We need, however, 2 position points and time measurements, at least, to make an estimate. One way to make this estimate is to take the first 2 position data points and corresponding times. So we can do that. Go to Tracker and look at the second time, 0.003 seconds, and at that time the position of the ball is at x equals minus 0.028 meters. So we can go ahead and record that and use that information to calculate what the average velocity is, the initial velocity, by computing delta r over delta t. The second position data point minus the first position data point divided by the corresponding change in time. And when we do that for this analysis, we find an average velocity of the ball initially of 0.88 meters per second in the minus x direction. Now, one more piece of information. Let's note the time of the last observation in the motion we analyzed. We see that time is 0.734 seconds. So we can record that here as well. Now, we need all this information to construct, using Newton's second law, a model to predict the motion we've analyzed here. That's the subject of our next lecture.